Hello, this is Yan Xie, and here's my report for Lab 4. The purpose of this lab is to create circuits and measure their current and potential differences, and computing the time constant of an RC circuit. Some fundamental physical principles involved in this lab include Ohm's law, energy conservation, the loop rule, and the knot rule. My result for this lab is a time constant of 6 seconds. In the first section, we are shown a simple series circuit as indicated in the diagram on the left. We are asked to predict the current I1 and I2. Using Ohm's law and the loop rule, the current for a series circuit should stay constant and can be calculated by dividing V by R. Thus, my prediction for both I1 and I2 is 3 over 147 equals 0.02 amperes. After simulating this circuit in the circuit construction kit, my prediction is proved to be right. When I reverse the connections to one of the ammeters reads the same. Next, I replace one of the ammeters with a voltmeter. The voltmeter reads 3 volts, while the ammeter reads 0 amperes. 2 meters read this way because in this open circuit, current is not flowing through the loop. Therefore, the voltmeter measures the voltage difference between the positive and negative ends of the batteries. In this slide, I have closed the circuit with a wire and remeasured the potential difference for each part of the path around the circuit. The sum of the individual potential differences for a round trip around the circuit should be 0 according to the conservation of charge or the knot rule. My measured differences actually add up to 0. Notice that when I attach the voltmeter, I alter the circuit, but the ammeter reading does not change because the ideal voltmeter has infinite resistance, meaning that no current flows through the voltmeter. Here I replace the voltmeter with an ammeter in parallel with the 100 ohms resistor. The current through both ammeters read 0.06 amperes, meaning that the current no longer passes through the 100 ohms resistor. Using Ohm's law and the measurements in part 5 and part 6, I could calculate the resistance of each of the following circuit elements by dividing delta V by I. Resistance of the 47 ohms resistor equals 47.85 ohms. Resistance of the 100 ohms resistor equals 102.05 ohms. Resistance of the wire and ammeter equals to 0. In the last section of lab, I have constructed an RC circuit using a 10 ohms bulb, 1 9 voltage battery, and a 200 mF capacitor. When I first connect the battery to the capacitor and the bulb, I observed that the bulb lights up and then dims down. This is because the current in the circuit eventually stops. When I disconnect the battery and connect the capacitor directly to the bulb lights up until the capacitor is completely discharged. This time, current reverses its direction and stops after some time. Using the 10 ohms bulb, the capacitor takes 12.13 seconds to charge and 13.44 seconds to discharge. Using the 20 ohms bulb, the capacitor takes 24.95 seconds to charge and 29.81 seconds to discharge. Finally, I set up a circuit in the CCK with a 9V battery, a 200 mF capacitor, and a 30 ohms light bulb. I plotted 20 seconds worth of voltage versus time data on a ln of delta V over delta V naught versus t plot after setting the capacitor discharging. This plot yields a straight line with a slope of -1 over RC equals -0.1667, with RC being the time constant of the circuit. RC is then calculated to be 6 seconds. If I were doing this lab in real life, ammeters would read lower currents than if there was no ammeter. This is because an actual ammeter has a resistance, whereas an ideal ammeter does not. In addition, it would take much longer to charge a real capacitor using a real battery, as they both have some internal resistance that slows down the process. Thank you.